Section 1, Introduction to Custom Blueprints. Next, we're adding some danger to the catwalks in Room 3 with custom block traps. To build these, we need to move beyond the standard setups we've used so far. You've already seen the character and level blueprints in action, but now we're going to step it up. We're going to create a brand new blueprint class from scratch. Think of a blueprint as a container. It bundles various assets and actors into a single, interactive object that Unreal can recognize. To get started, we'll open the content drawer and dock it into the layout so it stays visible while we work. To keep things organized, we'll start by creating a dedicated folder. Right-click in the content drawer, select New Folder, and name it Blueprints. Once that's set, jump into that folder, right-click again, and select Blueprint Class to begin. Under the Create Basic Asset menu, select Blueprint Class. A window will pop up asking you to choose a parent class. Essentially, you're deciding what this object is. We're going with a standard actor, which is a general-purpose object you can place anywhere in your level. Alternatively, you could choose a pawn, which is an actor that can handle input from a controller. Think of things like vehicles or simple AI. Below that is the character class. This is a specialized pawn designed with built-in movement like walking and jumping. This is exactly what our player character uses. For now, though, we'll stick to the basics and ignore the more advanced options at the bottom. While there's a drop-down for more complex options, the most common classes are listed right up front. Since an actor is a versatile object that can be spawned or placed anywhere in your world, it's the perfect choice for this. It's the most flexible, foundational blueprint you can build, so let's select that to move forward. Click Actor to generate the class, then give it a name. Let's go with BP Falling Block and hit Enter. Now that the blueprint is ready, try dragging it into the scene. You'll see a placeholder icon appear. That's just Unreal's way of telling you the blueprint is currently empty. Right now, the blueprint is just a blank slate, no mesh, no code, nothing. Let's change that. Double-click to open it. If this is your first time, you might see a simplified window with a message saying this is a data-only blueprint. This just means there are no components or scripts added yet. To get to the full editor, click the link at the top that says Open Full Blueprint Editor. Because there are no scripts or assets inside yet, Unreal simplifies the view to only show default settings. Since the blueprint isn't using any advanced features yet, it hides the extra windows to stay clean. To switch back to the standard layout, just click Open Full Blueprint Editor at the top. This brings back your workspace so we can start building. We're back to the standard editor view. If you compare this to the third-person character, you'll notice the layout is identical. You have your components, variables, and functions on the left, the event graph and viewport in the center, and your details panel on the right. The only difference is that this one is still a blank slate, waiting for us to fill it in. To give this trap some weight, we'll start by adding a static mesh. Remember, a static mesh is essentially the physical 3D model that players will see and interact with in your game. For this trap, we obviously need a block. To add it, head over to the Components tab and click the Add button. Select Static Mesh from the list. You can rename it if you want, but since this trap only uses one mesh, leaving it as the default is perfectly fine. Just hit Enter to confirm. If your blueprint had several meshes, naming them would be a must to keep things organized. Even though we've added the static mesh component, you'll notice the viewport still looks empty. That's because we've only created the slot for a mesh. We haven't actually assigned a 3D model to it yet. To see the block, we need to pick a specific asset to fill that empty space. To fix that, select the static mesh in the components list and head over to the details panel. If you've accidentally closed any of these panels or can't find them, don't worry. Just go to the Window tab at the top of the screen. You can restore the Details pane, Components list, or any other missing window from there. We'll use a basic cube as our placeholder. We'll swap this out for actual art assets later, but for now, we just need something solid so we can see and test the trap in-game. In the Details panel, find the Static Mesh section. You'll see a slot currently set to none. Click that to open the Asset Picker. Click the drop-down to see every mesh available in your project, including the ones that came with our template. I'm going to use a basic one from the third-person starter content called SMCube. Select that, and you'll finally see our block appear in the viewport. Zoom out in the viewport, and you'll see the cube is finally there. At this stage, the blueprint doesn't have any logic yet, so it's essentially just a standard static mesh. Before moving forward, hit compile and save. I also like to click and drag the blueprint tab to dock it right next to the main level tab. This makes it much faster to jump back and forth between editing the block and testing it in the world. Since I already placed the blueprint in the level, it's now updated with the cube mesh. It looks a bit small though, so I need to check the scale against our character. To do that, I'll delete the player start from the first room and move it here to room 2. This way, I can spawn right next to the cube. I'm also going to add some light to the area since it's currently a bit too dark to see clearly. I'll drop an erect light by going to the Place Actors tab. Once it's in the scene, I'll hit E to bring up the rotation tool, snap it 90 degrees so it faces down like a ceiling light, and pull it up to the center of the roof. To adjust the coverage, I'll head to the Details panel and tweak the source width and source height settings to get the lighting just right. I'll scale these values until the light source roughly matches the size of the ceiling. Even with that done, it's still looking a bit dim in-game. To fix this, I'll crank up the intensity. I can either shift the light's position or just boost the default value. Right now, it's set to 8 candelas, which is basically the equivalent of 8 candles, so I'll slide that slider up until the room is properly lit. It's still looking a bit dark, so I'm going to set the light to movable for a quick fix. That should make things clear enough to work. Now, looking at the block, it's definitely too small. It needs to be about twice this size. While you could scale it directly in the level editor, there's a better way to handle this. Scaling directly in the level is fine if you're just eyeballing the size, but there's a major downside. If you drag out a second copy of the blueprint from your content browser, it will revert to the original small size. That's because you've only modified that specific instance in the world, rather than updating the master settings for the object itself. To ensure every trap we place is the correct size, we need to make the change inside the blueprint editor instead. To fix this for every block we use, we need to adjust the blueprint's default scale rather than just a single copy. If you remember our previous work with static meshes, this concept of defaults should feel familiar. First, I'll select the instance in the level and hit the reset icon next to the scale in the Details panel. This snaps it back to its original size, so we're starting with a clean slate. Updating the blueprint defaults. Instead of scaling it in the level, go back into your BP Falling Block editor window. Select the static mesh component on the left. In the Details panel, look for the scale settings. Set the values to 2 for X, Y, and Z. Now, when you hit compile and save, every instance of this block in your world, and any new ones you drag out later, will automatically be at that larger, uniform size. This keeps your workflow clean and prevents you from having to resize every single trap manually. To update the master version of the trap, head back into the BP Falling Block editor. Select the static mesh in the components list. In the Details panel, find the scale settings. Change the X, Y, and Z values to 2. By doing this inside the blueprint, you're setting a new default. Now, every time you drag this block into your level, it will automatically spawn at the correct, larger size without you having to touch the scale settings again. Go ahead and compile and save to apply those changes to your scene. You can type in 2 for each box manually or just click the lock icon to enable uniform scaling. With the lock active, changing one value updates all of them instantly, keeping the proportions perfect. Once that's done, hit compile and save to lock in the changes. Back in the level editor, you'll see the block has automatically updated. Now, if you drag out a second copy, it spawns at that new, larger size by default. This is the real power of blueprints. You can set universal defaults for your objects while still retaining the flexibility to tweak individual instances in the world whenever you need a unique variation. This flexibility is great because it allows you to have multiple traps that share the same logic but look different. If you needed one specific block to be massive or tiny, you could just scale that single instance in your level without affecting the others. Blueprints allow for this perfect balance between global settings and individual tweaks, which really speeds up your workflow. However, since we want all our traps to be uniform for now, let's head back into the editor and keep moving forward. Now we need to get this block off the ground so it can actually fall on the player. You might think the easiest way is to just grab it in the level editor and pull it up, which works fine for a static object. However, I'm going to handle the height a bit differently. Since we need this trap to actually detect when a player is running underneath it, we're going to build that logic directly into the blueprint. This way, the height and the trigger stay synced up perfectly. Since this block should only drop when the player is directly beneath it, we need a way to detect that movement. Think back to the Kill Z volume we used earlier. That was essentially an invisible box that triggered an action the moment the player stepped into it. We're going to apply that same logic here by adding a trigger volume to our trap, which will act as the sensor to set the whole thing in motion. To set this up correctly, we need an invisible volume separate from the cube itself that the player can walk through to trigger the trap. Instead of manually raising the block in the level editor, keep the blueprint aligned with the floor where you want the trap to be triggered. We'll go into the BP falling block editor and move the cube up by about 300 units, which is 3 meters in Unreal Engine. By moving the mesh inside the blueprint, we create a gap between the origin of the blueprint at floor level and the actual physical block. This leaves the perfect space for us to add our trigger volume right at the base. Moving the mesh in the blueprint. Open your BP falling block blueprint. Select the static mesh component. In the Details panel under Transform, look at the location settings. Change the Z value to 300. Now, in your viewport, you'll see the mesh hovering in the air while the scene root, the little white sphere or crosshair, stays on the ground. That ground point is where we'll place our sensor. By increasing your grid snap to 100 and moving the mesh up 3 units, you've precisely positioned it 300 units high. In a blueprint, the location of the default scene root, that white sphere icon at 0, acts as the anchor or pivot for the entire object. Even though your cube is now hovering in the air, Unreal still considers the location of the trap to be wherever that root is. This is a huge advantage for us. It means you can drag your blueprint onto the floor in the level editor, and the block will automatically be preset to hang 3 meters above that spot. Now that we have that empty space between the floor, the root, and the ceiling, the mesh, we have the perfect place to put our detection sensor. Exactly, this is the beauty of local versus world space. By moving the mesh relative to the root, you've essentially told the blueprint, wherever I am placed in the world, my cube should always hang exactly 3 meters above that spot. It makes level design incredibly efficient. Instead of manually positioning each block in the air and then manually positioning a trigger on the ground, you just drag the blueprint onto the catwalk. The feet of the blueprint stay on the floor, and the head, the block, is perfectly preset to crush whoever walks below. Adding the detection sensor. Now that the mesh is hovering, we need to fill that empty space with a sensor. In the Components panel, click Add. Search for and select a box collision. Name it something like Trigger Volume. Adjusting the trigger. You'll see a wireframe box appear at the root. We want this box to act like a tripwire across the catwalk. Scale it up, use the Scale tool R or the box extent settings in the Details panel so it covers the width of the path and the height of the gap. Keep it on the floor. Since the root is at ground level, your collision box is already perfectly positioned to catch the player's feet as they walk by. Now, whenever the player's character overlaps with this invisible box, we can tell the blueprint to let the cube fall. To create the sensor for the trap, we'll add that box collision now. These are perfect for gameplay logic because they are completely invisible to the player but act as a physical tripwire in the engine code. Adding the collision component. In the Components panel, click Add and type Box. Select Box Collision from the list. I'm going to rename mine to something like Trigger Volume so it's easy to identify later when we start coding the logic. Positioning the sensor. By default, the box will appear at the scene root 0, which is exactly where we want it, right on the ground. However, it's currently a bit small. Size it up, use the Scale tool R, or adjust the box extent in the Details panel. The goal: you want this box to be wide enough to cover the entire catwalk so the player can't sneak past it, and tall enough that the player's character model definitely overlaps with it when they walk through. Now we have a clear setup. The cube is hovering 3 meters high and the box collision is sitting on the floor waiting for the player to arrive. Adjusting your alignment in the orthographic left view is a smart move. It takes the guesswork out of positioning. Since the cube's pivot point is in the corner rather than the center, it's currently sitting offset from our scene root. By switching to the left view, you can see the exact wireframe relationship between the root, where the trigger will live, and the mesh. Aligning the mesh and root. Shift the static mesh. While in the side view, slide the cube along the x-axis until it is centered directly over the root icon. Verify the gap. This ensures that when the player walks right over the origin of the blueprint, the block is hanging perfectly overhead, ready to drop straight down. Sizing the trigger volume. Now that the cube is centered, select your box collision again. We want to match the footprint of the block. Box extent. In the Details panel, you can manually adjust the box extent values X, Y, and Z. Pro tip: if your cube is scaled to 2, it's roughly 200 units wide. Setting your box extent to 100, since extent is measured from the center out, will make the trigger perfectly match the width of the block. The tripwire height. Keep the Z extent high enough to catch the player's torso, but keep it centered on the floor so it acts as a floor-level sensor. Once those are aligned, your blueprint setup is physically complete. You've got the trigger on the floor and the block perfectly centered 3 meters above it, ready to start making it actually fall. Switching the snapping to 10 gives you that much-needed precision to line things up perfectly. Since you're in the left view, you can see exactly how the box overlaps the path. Here is the best way to finalize that alignment. 1. Match the width. With the Scale tool R active, pull the red X or green Y handles until the edges of the box collision line up with the outer edges of the static mesh above it. This ensures that if the player's shoulder even grazes the danger zone, the trap will trigger. 2. Adjust the height Z-axis. Scale the box vertically so it sits comfortably on the catwalk. You don't need it to be 3 meters tall, just high enough to ensure the player's character model, the capsule component, can't jump over it or slide under it without a collision. 3. Check the footprint. Now toggle back to the perspective view or the top view. You should see a wireframe box on the floor that looks like a shadow of the cube hanging above it. Ready for logic. Now that the physical setup is done, your blueprint looks like a complete trap unit. Scene root at the base 0. Box collision centered and sized to the catwalk. Static mesh hovering 300 units high. Now we just need to tell the engine, when the player enters this box, turn on physics for the cube. Do you want to jump into the event graph to start the scripting, or do you want to double-check the collision settings first? Getting that alignment right in 3D space can be tricky when you're only looking at it from one side. Even if it looked perfect in the left view, switching back to perspective often reveals that the depth, the y-axis, or the positioning is a bit off. Since we want this trap to be unavoidable, we need to make sure that box collision fully spans the tunnel the player walks through. Finalizing the volume alignment. Check the depth. In perspective mode, rotate your camera around the block. If the box is skinny like a piece of paper, the player might run right past it. Use the Scale tool R to pull the green handle until the box is as deep as the cube. Close the gap. You mentioned spanning the height from the mesh to the floor. Make sure the bottom of the box is sitting flush with or even slightly below the scene root. If there's a gap between the floor and the bottom of the trigger, a crouching player might sneak through. The safety buffer. It's actually okay if the box collision is slightly wider than the cube. It's better to have a trap that's a little sensitive than one the player can wiggle past by hugging the wall. Pro tip: the center trick. If you're struggling to line them up perfectly, look at the location values in the Details panel. If your static mesh is at X, 0, Y, 0, Z, 300, your box collision should likely be at X, 0, Y, 0 as well. Then just adjust the box extent Z so it fills that 300 unit void. Once that wireframe box looks like a solid wall of invisible energy filling the space under the cube, hit compile and save. You've officially built the hardware. Now we just need to wire the brain in the event graph. Ready to make this block actually drop. Using the top view is the most reliable way to ensure you haven't left any safe zones for the player to squeeze through. By centering the box collision and scaling it along the y-axis, you've effectively created a complete footprint that matches the cube's dimensions perfectly. Now that your setup is perfectly aligned, the static mesh is hovering at Z equals 300. The box collision is centered at the origin, spanning the width and depth of the path. The scene root remains at the ground level, acting as the anchor for the whole trap. When you look at it in the perspective view now, it should look like a tidy, professional unit. This is the hardware phase of the blueprint. The physical components are all in place. The next step: adding the brain. The box is there, but currently it doesn't know it's supposed to do anything. We need to move from the viewport tab to the event graph tab. We are going to create a script that says, Event: when an actor, the player, begins an overlap with this box collision. Action: target the static mesh and set simulate physics to true. Since the mesh is hovering in the air, the moment physics is enabled, gravity will take over and boom, you have a falling trap. Are you ready to head into the event graph and wire up your first bit of collision logic? That perspective view really confirms that the trap is ready to go. The wireframe box effectively acts as a sensor field between the floor and the block. Since the box collision is invisible in-game, that overlap with the mesh or the floor doesn't matter for the player's experience. It actually ensures there are no dead zones where the player could potentially walk through without the sensor picking them up. Preparing for the drop. Now that the physical setup is solid, we need to address why that block is staying in the air. By default, objects in Unreal Engine are static or kinematic. They don't fall unless we tell them to respect gravity. To make this work, we're going to use the Simulate Physics toggle. However, if you turn it on right now in the Details panel, the block will just fall as soon as the game starts. We want to wait until that box collision is triggered. The logic plan. We are about to head into the event graph to connect these two pieces. The logic will look like this. The component, the trigger volume box collision. The event, on component begin overlap. The target, the static mesh. The function, set simulate physics. Before we switch tabs, make sure you have the box collision selected in the components list. Down at the very bottom of the details panel, you'll see a list of green buttons for events. Shall we click that on component begin overlap button and start the script? Exactly, you've hit on a key concept in Unreal Engine, collision versus triggering. Even though it's called a box collision, we are using it as a trigger. In Unreal's physics engine, an object can either block like a solid wall or overlap like an invisible sensor. Because this volume is set to overlap, it won't stop the player's movement or cause the block to bounce off it. It simply sends a signal the moment something enters its bounds. Final sanity check before the event graph. Before we start the coding, let's make sure the sensor is actually listening for the player. Select the box collision in your components list. In the details panel, scroll down to the collision section. Check the collision presets. It should typically be set to trigger or overlap all dynamic. Why? If it's set to block all, the player will hit an invisible wall instead of walking through the trap. Ensure generate overlap events is checked. It usually is by default. To the event graph. Now that our tripwire is physically in place and set to overlap, we are ready to wire it up. Click the event graph tab at the top of the window. Look for a clean space in the graph. With your box collision still selected in the components list, right-click in the empty graph space. Search for Add-on Component Begin Overlap. This node is the ear of your blueprint. It's constantly listening for the moment the player steps into that box, ready to tell it what to do next. That is the exact reason why blueprints are so powerful. Instead of managing a floating cube and an invisible sensor as separate, loose items in your level, you've created a single, cohesive gameplay unit. When you drag BP falling block around your level, the trigger and the mesh stay perfectly synced. If you decide the trap needs to be higher, you change it once in the blueprint editor and every single trap in your level updates instantly. Understanding the component relationship. In your components hierarchy, you likely see something like this. Default scene root, the anchor on the floor. Static mesh, the weight hovering at Z equals 300. Box collision, the sensor sitting on the floor. Because the mesh and the box are children of the scene root, they follow it everywhere. It's like having a backpack wherever the person, the root goes, the contents, the mesh and collision go to, maintaining their relative distance. The final step, wiring the trap. Now that the body of the trap is built and positioned, it's time to give it a brain. We want to tell Unreal, when the player overlaps the box, turn on physics for the mesh. Open the Event Graph tab in your Blueprint editor. With your box collision selected, right-click in the graph and select Add Event on Component Begin Overlap. Drag a wire from the static mesh component into the graph to create a reference node. Drag off that mesh node and search for Set Simulate Physics. Connect the Overlap execution pin to the Set Simulate Physics node and make sure the Simulate checkbox is ticked true. Once you compile, you'll have a fully functional hazard. Are you ready to see that block come crashing down in the simulator? Right now, the blueprint has the hardware, the sensor, and the block, but it lacks the intelligence to know who is triggering it. Just like our Kill Z volume, we need to make sure the trap doesn't just fall for any random object. We want it to specifically react to the player. To do this, we need to use a technique called casting. This allows the blueprint to check if the thing that just walked into the box is actually our player character and not, for example, a physics prop or a stray projectile. Step 1. Creating the overlap event. In your event graph, we need to grab the event that fires the moment something touches that box. Select your box collision in the components list. In the Details panel, scroll all the way to the bottom to the Events section. Click the green plus button next to On Component Begin Overlap. This will drop a large red node into your graph. This node is the trigger for everything that follows. Step 2. Identifying the player. The overlap node has a pin called Other Actor. This represents whatever just stepped into the box. We need to interrogate that actor to see if it's the player. Drag a wire off the Other Actor pin. Type Cast to Third-Person Character or whatever your specific player character blueprint is named. Connect the Execution pin, the white arrow from the overlap node to the Cast node. Step 3. Triggering the physics. Now that we've confirmed it's the player, we tell the block to fall. Drag your static mesh component from the left-hand list directly into the graph to create a reference. Drag a wire off that mesh node and search for Set Simulate Physics. In that new node, make sure the In Simulate checkbox is checked, set to true. Connect the top execution pin of the Cast to node to the Set Simulate Physics node. The result: when you hit compile and save, you can test it out. When your player walks through the invisible box on the catwalk, the cast will succeed, the script will fire, and the block will suddenly switch from a static object to a physics object, sending it crashing down toward the floor. Are you seeing the block drop when you walk under it, or is it staying stubbornly in the air? Exactly. By starting with Event Begin Play, you are essentially telling the blueprint, as soon as the game starts, go find exactly who the player is and keep that information ready. This is a very efficient way to handle it. Instead of the blueprint having to guess who just walked into the trap every single time, it already has a direct reference to your specific character. Setting up the reference. Here is how you'll wire that initial handshake between the trap and the player. Event Begin Play. This node is already in your graph by default. Get Player Character, drag off the execution pin and add this node. Since this is a single-player game, Player Index 0 is exactly what you want. Cast to Third-Person Character. Drag off the return value of the Get Player Character node and search for your specific character class. Promoting to Variable. To make this really useful for our box collision logic later, we should save this result so we don't have to cast again. Right-click the As Third-Person Character pin on the right side of the Cast node. Select Promote to Variable. Rename this variable to something like PlayerF. Why this matters for the trap. By doing this on Begin Play, you've created a VIP list with just one name on it, the player. Now when we move down to our On Component Begin Overlap event for the box collision, we can simply compare the other actor, the thing that touched the box, to our PlayerF. If they match, we fire the physics. If a random physics prop or an NPC rolls into the box, the trap won't accidentally trigger and waste its one big crush moment. Ready to connect that PlayerF to the box collision event. You're absolutely right to prioritize efficiency here. In game development, especially as your levels get more complex, minimizing expensive operations is key to maintaining a smooth frame rate. Casting is essentially a type of check where the engine asks, "Are you this specific thing? Okay, if so, let me look at all your specific variables and functions." Doing that every single time a collision occurs, especially if you have dozens of these traps, can add up. By doing it once at Begin Play and storing that reference, you're just doing a simple comparison later, which is much cheaper for the CPU. Completing the Begin Play logic. Now that you've performed the cast, let's make sure that information is stored so the box collision can use it later. Promote to Variable. Right-click the output pin, the blue one labeled as Third-Person Character on your Cast node. Select Promote to Variable. Name it in the variables list on the left. Rename it to something like Player Reference. Wiring the trigger logic. Now let's jump down to your On Component Begin Overlap Trigger Volume event. Instead of casting again, we do a quick check. Get Player Reference. Drag your new Player Reference variable from the list on the left into the graph and select Get. Comparison. Drag a wire off the Other Actor pin from the Overlap event and type ===. Connect them. Plug your Player Reference into the second slot of that equals node. Branch. Hold B and click in the graph to create a branch node. Connect the equals output to the red condition pin. Execution. Connect the white execution pin from the overlap node to the branch. The drop command. Now the final piece of the puzzle. From the true pin of your branch, drag out and search for Set Simulate Physics. Target your static mesh. Make sure the simulate box is checked true. Now, when the game starts, the trap memorizes who the player is. When anything walks into the trigger, it quickly asks, "Is this the player I memorized?" If the answer is yes, the block falls. Does it feel more responsive now that you've optimized the logic? Exactly. That variables panel is your blueprint's memory bank. In a level blueprint, variables are global to the map, but here in the actor blueprint, they are specific to this falling block object. As you noticed, Unreal neatly organizes the panel so you can distinguish between components, the physical parts of the actor, the cube, the box collision, the root. Variables, the data or references you've created, like your player ref. Finalizing the drop logic. Now that you have your player ref saved, we can finish the trigger. Instead of a heavy cast operation every time the player touches the box, we'll use a simple branch. Drag and drop, grab your player ref variable from the list and drop it into the graph. Select Get. Compare, drag a wire off the other actor pin from the overlap event and type ==. Plug your player ref into the bottom of that node. The filter, connect that == node to a branch shortcut, hold B and click. This ensures only the player can trigger the trap. Gravity on, from the true pin of the branch, drag out and search for set simulate physics static mesh. Make sure the simulate box is checked. The single use factor. One thing to keep in mind, as it stands, the block will fall the first time you walk under it. If you want to reset the trap or prevent it from trying to fall again while it's already on the ground, you might eventually want to add a do once node. But for now, hit compile and save. Your trap is officially armed and ready for a test run. Does the block fall exactly when you step into that wireframe box? That is a fantastic analogy. Thinking of a blueprint as a self-contained file folder is exactly how you should visualize it. While the level blueprint acts like the manager of the entire office, seeing everyone at their desks and knowing where the furniture is, an actor blueprint is like a specialized worker who only knows what's inside their own briefcase. Why this isolation is actually a superpower. It might feel restrictive at first that you can't just click on the floor mesh in your level and reference it inside BP falling block, but this isolation is what makes your workflow so fast. Portability, because the folder is self-contained, you can migrate this BP falling block to a completely different project and it will work perfectly because it brings its briefcase, the mesh, the trigger, and the player checking logic with it. Scalability, if the blueprint were hard-coded to look for catwalk piece 52 in your current level, it would break the moment you dragged it onto a different platform. By keeping it unaware of the level, it works anywhere you drop it. Communicating outside the folder. Since the blueprint is a closed folder, it has to use specific phone lines to talk to the outside world. Casting, the handshake, as we did with get player character cast to third-person character, we are essentially saying, I don't know who is out there, but if the person I just bumped into matches this specific ID badge, I'll talk to them. Variables, the memory. By saving that player ref, you've taken information from the outside and tucked a copy of it into your folder so you can refer to it whenever you want. Ready for the big test. Now that the logic is tucked inside the folder and the trap knows who to look for, compile and save one last time. Go back to your level editor. Drag a few more instances of BP falling block onto the catwalk. Press play. As you run under them, each individual folder will independently check. Is this the player? Yes. Drop the block. How does it feel to see your self-contained logic working across multiple instances in the level? That's the perfect way to wrap your head around it. By grouping those nodes and setting them aside, you're keeping your begin play logic clean, essentially setting up the ID check before the actual workday starts. Now that you've got your player ref tucked away in its variable slot, we can move on to the actual action part of the trap. Since the blueprint now knows who the player is, we just need to compare that reference to whoever walks into our box collision. Wiring the trigger logic. Find your overlap event, go to the on component begin overlap trigger volume node we created earlier. The who is it check, drag your player ref variable from the left-hand panel into the graph and choose get. Comparison, drag a wire from the other actor pin on the overlap node and type == to get the equal object node. Plug your player ref into the bottom slot. The filter, drag off the execution pin of the overlap node and create a branch or hold B and click. Connect the output of your == node to the condition of that branch. Dropping the hammer. Now for the satisfying part. From the true pin of that branch, which only fires if the player is the one who stepped in the box. Drag your static mesh component into the graph. Drag a wire off it and search for Set Simulate Physics. Make sure the Simulate checkbox is ticked true. Once you compile and save, go ahead and hit play. When you walk through that invisible volume, the blueprint will check its folder, see that it's you, and finally let that block drop. Does the block fall at the right moment, or is it giving you any trouble? That's exactly right. Unreal gives you multiple paths to the same destination. Whether you right-click in the graph or use the big green buttons in the Details panel, you're essentially telling the engine, I want to create a specific moment in time for this specific component. Why the Details panel is often faster. Using the buttons at the bottom of the Details panel is a great habit to get into because context sensitivity, it only shows events that actually apply to a box collision like on-component begin overlap. You won't get distracted by physics events or input events that don't make sense for a trigger volume. Automatic naming. When you click that green plus button, Unreal automatically jumps you to the event graph and creates the node with the correct name and all the necessary pins like other actor and sweep result already built in. Setting up the overlap logic. Since you've got your playeref variable ready and grouped to the side, let's finish the connection. Click that plus next to on component begin overlap. In the event graph, you'll see your new red node. The comparison, drag out from the other actor pin and search for the equal node. The reference, drag your playeref variable into the graph, select get, and plug it into the bottom of that equals node. Completing the crush command. Now, just like we planned, we use a branch to act as our gatekeeper. Connect the overlap execution pin to a branch node. Plug the output of your equals check into the condition. From the true pin, drag in your static mesh and call the Set Simulate Physics function. Pro tip: grid alignment. Once you've wired this up, take a look at your level editor. Since you aligned everything to the grid inside the blueprint, you can now hold Alt and drag your trap to duplicate it perfectly along your catwalk. Every single copy will independently wait for the player to trip that invisible line before dropping the block. Does the block successfully fall when you test it out in the viewport? You're absolutely right. The box collision is like the Swiss Army knife of triggers compared to the basic Kill Z volume. Because it's a component you can stick inside any blueprint, Unreal gives you much more granular data about what's happening the moment that overlap occurs. Looking at that node, you'll see pins like other actor, other comp, and sweep result. These allow you to do some really advanced logic later on, like checking if the player hit a specific side of the box, but for our trap, the most important one is other actor. Wiring the detection. Now that the node is in your graph, let's use that playeref you created earlier to finish the brain. The comparison, drag a wire off the other actor pin and type equals. The memory, grab your playeref variable from the list on the left, drag it in, select get, and plug it into the bottom of that equals node. The gate, add a branch node, hold B and click. Connect the white execution pin from on component begin overlap to the branch. Connect the red Boolean output of your equals node to the condition pin. Flipping the physics switch. Now the final payoff. Drag your static mesh, the block, from the components panel into the graph. Drag off the mesh node and search for Set Simulate Physics. Crucial step, in that node, make sure you check the box for in Simulate so it's set to true. The final result. When you walk into that volume, the system checks if the other actor is your playeref. If it is, it flips the switch on the block's physics. Since it's hovering 3 meters in the air, gravity will take over instantly. One quick tip, since we want this to be a one-time gotcha moment, you might notice that if you walk back and forth, the engine keeps trying to turn on physics for a block that's already on the ground. It doesn't hurt anything, but if you want to be extra clean, you can put a do once node right after the branch. Ready to hit compile, save, and go for a run across that catwalk. Exactly, you've nailed the distinction. A Kill Z volume is like a specialized tool. It's pre-programmed with a specific job, destroying actors. Using a box collision is like starting with a blank canvas. It's more flexible, but it relies on you to provide the instructions for what happens during that interaction. Because we are using this generic version, we have to manually define the what, the who, and the how. The final handshake. Since you've already created the playeref and added the on component begin overlap node, you're ready to finalize those instructions. Identify the who, drag off other actor, and use the equals node to compare it to your playeref. Filter the when, use a branch node. If the player is the one who entered the volume true, the logic proceeds. Execute the how, drag in your static mesh and use the Set Simulate Physics node, set to true. Why this is better than a specialized volume. By using this generic approach inside a blueprint, you've actually made the trap more intelligent than a standard kill Z volume. Precision, it only drops when the player is there, not when a stray physics prop rolls by. Customization, you could easily add a sound effect, a particle puff of dust when it hits the ground, or even a camera shake, all triggered by that same overlap event. Give it a test run. Once you've connected those 3 nodes, branch right arrow, set simulate physics right arrow, target, static mesh, hit compile and save. Go ahead and jump into your level. If everything is wired correctly, as soon as your character crosses that invisible line on the catwalk, the mesh should lose its static status and come plummeting down. Are you getting a satisfying thud when you walk under it? That logic is rock solid. By ignoring the false path, you are essentially telling the blueprint, if a stray physics prop, a projectile, or even another falling block triggers this sensor, just ignore it. This keeps the trap armed specifically for the player's arrival. Now that your branch is acting as the gatekeeper, it's time to wire up the payload to the true output. Activating the trap. Select the payload from your components list on the left, drag your static mesh, the cube, into the event graph. This creates a reference node so the code knows which object to move. Toggle physics, drag a wire off that mesh reference and search for set simulate physics. Enable gravity in the new node, ensure the simulate checkbox is checked, set to true. Connect the logic, connect the true pin of your branch to the input execution pin of the set simulate physics node. Final step, testing the scale. Once you hit compile and save, go back to the level editor. Since you have a single blueprint, try placing 3 of these in a row along your catwalk. What to look for during playtest. The drop, does the block fall the moment your character's capsule enters that wireframe box? The impact, does it hit the catwalk and stop, or does it bounce? Since physics is now on, it will behave like a real-world object. The reset, notice that once it falls, it stays there. If you want it to disappear or reset later, that would be our next step. How does the weight of the trap feel when it drops? Is the 300-unit height giving the player enough or too little time to react? Smart move. Using a print string is the best way to peek under the hood and verify that your logic is firing exactly when you expect it to. It's the standard sanity check in Unreal Engine to ensure your variables are matching up before you commit to the actual physics simulation. Adding the debug check. Break the wire, Alt+click, currently going from your true pin to the set simulate physics node. Drag off the true pin and search for print string. In the in string box, you can type something like trap triggered, or keep your comparison value to see that true message. Reconnect the logic, drag the execution wire from the end of your print string into the set simulate physics node. This way you get the message and the action at the same time. What to watch for in the viewport. When you hit play and run through the trap, top left corner, you should see your text pop up in blue. The timing, does the text appear the exact millisecond you step into the wireframe box? The filter, if you have any other physics objects in your level like a stray cube, try pushing it into the trigger. If your player logic is correct, the block should stay put and no text should appear. Final polish, making it dangerous. Now that the logic is verified, you've confirmed that. Begin play successfully found the player. The overlap successfully identified the actor. The branch successfully filtered the result. If the block is falling and the print string is firing, your hardware and software are perfectly synced. Are you happy with the speed of the fall, or do you think the block needs a bit more heft, mass in the physics settings to make it feel more threatening? This is where we transition from simple logic to actual physics. To make the trap function, we need to bridge the gap between our static mesh, which is currently just a decorative piece of the blueprint, and the physics engine. As you noted, we want that box to travel from its starting position at the top and plummet to the floor. In Unreal, there are 2 primary ways to move things: timelines interpolation, smooth, controlled movement, or physics, natural, gravity-based movement. For a falling trap, simulate physics is usually the most satisfying choice because it gives the object real weight and allows it to thud or bounce off the player or the floor. Activating the drop. Reference the mesh. From your components list, drag the static mesh, the cube, into the event graph. Toggle the simulation. Drag a wire off that mesh node and search for set simulate physics. The trigger, connect the true pin of your branch where your print string currently is to the input of this node. Set the value, ensure the in simulate checkbox is checked. What happens logically? When that in Simulate box is checked, the Unreal Engine immediately removes the static anchor from that cube. Gravity, the engine's global gravity, usually minus 980 on the z-axis, takes over. Mass, the block will fall at a realistic speed. Collision, because it's now a physics object, it will automatically stop when it hits the floor or the player because of the collision settings we adjusted earlier. A small challenge to consider. Once you wire this up, you'll notice that the block falls perfectly, but it's a one-and-done trap. It won't go back up on its own. Test it out, compile, save, and run under the trap. Does the thud feel heavy enough? If it feels too light, we can go into the details panel of the static mesh and increase its mass in kg to make it feel like a truly dangerous industrial block. That is a very smart pivot. While physics is great for natural chaos, it can be a nightmare for level design. If that block has even a tiny bit of rotation when it hits the catwalk, it could bounce like a basketball, fly off the edge, and leave your trap empty for the next player. By using a timeline, you are moving from simulation to animation. You gain 100% control over the speed, the easing, does it start slow and speed up, and exactly where it stops. Why the timeline is the right tool. Predictability, the block will stop exactly where you tell it to every single time. Performance, timelines are much cheaper for the CPU than calculating real-time physics collisions. Direction, you can ensure it only moves on the z-axis, preventing any sliding or bouncing off the catwalk. Setting up the timeline node. Create the node, right-click in your event graph and type Add Timeline. Give it a descriptive name like falling animation. The trigger, connect the true pin from your branch, the one checking for the player, to the play from start input of the timeline. Note, use play from start rather than play to ensure that if the trap ever needs to reset, it begins at the top again. Open the editor, double-click the timeline node to open its internal graph. This is where we'll define how long the fall takes. Creating the fall curve. Inside the timeline editor, click the plus track button, usually an icon with an F, to add a float track. Name it alpha or fall progress. Length, set the length of the timeline to something quick like 0.5 or 0.8 seconds. A trap needs to be fast. Add keys. Right-click at time 0 and add a key with a value of 0. Right-click at time 0.5 or your end time and add a key with a value of 1. This simple 0 to 1 curve acts as a percentage. At 0%, the block is at the top. At 100%, the block is at the bottom. Now that we have this percentage moving over time, our next step is to use a lerp linear interpolate node to translate that 0-1 value into the actual world coordinates of your block. Ready to wire up the movement. Perfect. Selecting Add Timeline at the bottom of that search list is the right move. You'll notice it looks a bit different from your other nodes. It has a gold clock icon and a place for you to type a name. Naming it something like Drop Timeline or Blockfall TL is a great habit, especially as your blueprints get more complex. Step 1. Connecting the trigger. Before we dive into the timeline itself, let's wire it to your logic. Connect the true pin from your branch, the one verifying the player, into the play from start input of the timeline. Why play from start? If the player triggers it, then dies and restarts, play from start ensures the animation doesn't get stuck halfway through. It forces the block back to the beginning of the animation every time the event fires. Step 2. The timeline editor. Now double-click that new timeline node. This opens up a new tab that looks like a mini video editing suite. To make the block fall, we need to create a curve that describes the movement. Since we only need to move the block from point A, the air, to point B, the floor, a float track is the simplest and most efficient way to do it. Click the F+ icon in the top left to add a float track. Name the track Fall Alpha. Step 3. Setting the keys. Think of this as a graph where the horizontal axis is time and the vertical axis is value, 0 to 1. Key 1, right-click at the start 0 and select Add Key. Set time 0 and value 0. Key 2, right-click further along. If you want a fast fall, set time 0.5 and value 1. Length, make sure to change the length field at the top to match your second key, e.g. 0.5. Otherwise, the block will fall in half a second, but the blueprint will wait for 5 seconds to finish. Once you have that diagonal line going from 0 to 0.51, you've created a perfect mathematical fall. Ready to head back to the event graph to use this fall alpha value to actually move the mesh. Great choice on the name. connecting the true pin to play or play from start is the correct ignition for the animation. Now, to give this timeline its instructions, we need to define the movement curve. Think of this as a graph that tells Unreal, over this much time, change the position by this much. Step 1. Creating the track. Double-click your Blockfall timeline node. It will open a new blank tab. Click the F+ button, add float track in the top left corner. Rename the track to something like alpha or progress. This value will represent the percentage of the fall, 0 being the start, 1 being the finish. Step 2. Plotting the fall. We need 2 keys to create a path for the block. The start, right-click anywhere in the dark graph area and select Add Key to Curve Float. Set its time to 0 and its value to 0. The end, right-click again to add a second key. Set its time to 0.5 for a half-second fall and its value to 1. Match the duration at the top of the window, find the length field, change it from 5 to 0.5. This ensures the timeline finishes as soon as the block hits the ground. Step 3. Smoothing the motion, optional but recommended. Right now, the fall is linear, meaning it starts and stops instantly like a robot. To make it feel like it has real weight, select both keys, click and drag a box over them. Right-click on one of the keys and select User or Auto. This creates S-curves, interpolation handles. You can adjust them so the block starts falling slightly slower and hits the ground with maximum speed, which looks much more natural for a trap. Back to the event graph. When you click back over to your event graph tab, you'll notice your Blockfall node now has a new output pin called alpha, or whatever you named your track. This number will now smoothly count from 0 to 1 every time the player triggers the trap. Are you ready to use that number to actually slide the static mesh down to the floor? Your slide deck on interactive trap engineering in Unreal Engine is complete. I've designed it with a sleek, high-contrast consultant aesthetic to make the technical details pop. Take a look and let me know if you'd like any adjustments to the technical flow or visual style. Spot on! Using a float is essential here because movement isn't chunky, it's fluid. If we used whole numbers, integers, the block would teleport from 0 to 1 to 2 like a glitchy slideshow. With a float, we get all those tiny decimals in between 0, 1, 2, 0, 5, 5, 0, 99, which translates to a butter-smooth animation. Calling the track height is perfect because that's exactly what it's controlling. Plotting your coordinates. Think of this graph as your animation script. Since the x-axis is time, seconds, and the y-axis is your value height ratio, let's set the boundaries for this trap. The starting point. Right-click at the very beginning of the graph and select Add Key. Set time to 0 and value to 0. Logic at 0 seconds, the block has moved 0% of the way. The impact point. Add another key further to the right. Set time to 0.6 or whatever speed feels lethal to you and the value to 1. Logic, in just over half a second, the block will have moved 100% of its designated distance. The use last key rule. Look at the length box at the top, it probably still says 5. Change that to 0.6 to match your last key. If you don't, the block will fall quickly, but the blueprint will stay busy for another 4.4 seconds of silence. Pro tip: visualizing the curve. Right now, your graph might look like a tiny dot or a flat line. To see your work clearly, click the zoom to fit icons, the small horizontal and vertical arrows in the top toolbar. This will snap the view so your 0 to 1 curve fills the whole screen. Once you have that diagonal line, you've successfully created a mathematical slide, ready to head back to the event graph and tell the static mesh to follow this curve. That is the exact dashboard you need. Those time and value boxes at the top are your precision controls. While you can click and drag the keys around with your mouse for a rough feel, typing the numbers directly into those boxes is how you get professional-grade, frame-perfect timing. Setting your anchor points. Since we want this block to drop exactly when the player trips the wire, let's set the coordinates for a heavy drop feel. The first key, the loaded position. With that first key selected, highlighted in blue, go to the top boxes. Set time to 0 and value to 0. This tells Unreal, at the exact moment the player touches the box, stay at the starting height. The second key, the impact position. Right-click further to the right on the graph to add a second key. Set time to 0.6 for a quick snappy fall and value to 1. This tells Unreal, 0.6 seconds later be at the final destination. Refining the view. If your keys look like tiny specks or disappear off the edge of the screen, use these 2 shortcuts in the top toolbar. Horizontal zoom, left arrow icon, snaps the time axis to your keys. Vertical zoom up arrow icon snaps the value axis to your keys. Why we use 0 to 1. You might wonder, why are we using 1 instead of the actual height like 300 units? By using 0 to 1, we are creating a normalized value, a percentage. In the next step, we're going to use a node called a lerp linear interpolate. It will take your 0 to 1 and stretch it to fit whatever distance you want. This makes your blueprint much more flexible. If you decide later that the block should fall 500 units instead of 300, you don't have to change the timeline, you just change one number in the event graph. Are your keys locked in and ready to be wired up? You've hit on the most important conceptual leap in blueprinting, the difference between absolute values and relative values. If we typed 300, the actual height, into that value box, this timeline would only ever work for a 300 unit drop. If you moved the block higher later, the animation would look broken. By using 0 to 1, we are describing the state of completion. Defining the graph. Value 0, the start state, the block is at its original high position. Value 1, the end state, the block has finished its journey to the floor. Go ahead and set that first key to time, 0 and value 0. Why this is a mathematical slider. Think of this timeline as a dimmer switch on a wall. When the switch is at 0, the lights are off. When the switch is at 1, the lights are at full brightness. The switch doesn't know how many volts are in the wall, it just knows it's at 0% or 100%. We are going to use this 0 to 1 height value to drive a node called a lerp linear interpolate back in the event graph. Setting the second key. To finish the movement script, let's add that second point. Right-click and add a key. Set time to 0.5. A half second is a great danger speed. Set value to 1. Now you have a perfect diagonal line. At time 0.25, halfway through the animation, the timeline will output a value of 0.5. We will use that 0.5 to tell Unreal, move the block exactly 50% of the way down. One final housekeeping step. Before we jump back to the event graph, make sure to check the length box at the very top of the timeline tab. It defaults to 5. Change it to 0.5 to match your second key. If you leave it at 5, the block will fall in half a second, but the blueprint will stay active and playing for an extra 4.5 seconds of dead air. Ready to go back to the event graph and wire this slider to the actual mesh. That is a critical distinction to make. If you moved the root, the whole blueprint, your invisible trigger box would go crashing down with the block, which would probably result in some very strange behavior, like the trigger following the player's feet or never being able to fire again properly. By only moving the static mesh, the tripwire stays exactly where you put it in the level, while the weight does the moving. Step 1. Finding your A and B points. To make this fall look perfect, we need to know the starting height point A and the ending height point B. Go to your Viewport tab within the blueprint. Select your static mesh, the block. Look at the transform section in the details panel. Check the location Z value. If you followed the previous setup, it might be something like 300. This is your start. Now imagine it sitting on the floor of the blueprint. That value would be 0 or whatever height puts the bottom of the block flush with the bottom of the blueprint. This is your end. Step 2. The lerp logic. Now let's go back to the event graph. We are going to use a node that is the secret sauce of game animation, the lerp linear interpolate. Right-click in the graph and type lerp vector or lerp float. Since we are only moving the z-axis, a lerp float is the cleanest. The A pin start, type in your starting Z value, e.g. 300. The B pin end, type in your landing Z value, e.g. 0. The alpha pin, this is where the magic happens. Connect the height or alpha pin from your timeline directly into this. Step 3. Updating the mesh. The timeline is now acting like a conductor, sending that 0 to 1 value into the lerp, which calculates the exact height for every single frame of the fall. Drag a wire from the update pin of your timeline. Search for Set Relative Location Static Mesh. Right-click the new location pin on that node and select Split Struct Pin. This lets you see X, Y, and Z individually. Plug the output of your lerp into the new location Z pin. Why relative location? Because the mesh is inside the file folder, the blueprint relative location means distance from the center of the blueprint. By changing this, the block moves, but the blueprint itself and that all-important trigger box stays exactly where you placed it in the level. Does the math for your Z heights look correct in the details panel? You've spotted a classic blueprint gotcha. That indentation in the components list is telling you everything you need to know. The box is currently riding shotgun on the static mesh. If the parent, the block falls, the child, the trigger is going down with it. If you leave it like this, once the first block falls, the trigger box will be sitting on the floor. If a second player or the same player after a respawn walks through that area, the trigger won't be there to meet them. Fixing the hierarchy, the unparenting move. We need to make these two components siblings instead of parent and child. This way, they both exist inside the blueprint, but they can move or stay still independently. Click and drag in the Components panel, click on your box collision. Drop it on the root, drag it up and drop it directly onto the default scene root, the very top item in the list. Check the alignment, you'll know you've got it right when the box and the static mesh are aligned vertically in the list, no more indentation for the box. Verifying the locations. Now that they are independent, we need to make sure their starting points are still correct. The box collision should have a location Z of roughly 0 or wherever your catwalk is, it needs to stay put. The static mesh should have its location Z up at 300 or your desired height. Why this flat hierarchy is better? By attaching both components directly to the default scene root, you've created a much more stable folder. The root stays at the center of your blueprint. The trigger stays at the root, waiting for the player. The block can now use that set relative location node to fly up and down along the Z-axis without dragging the rest of the blueprint with it. Ready to set the movement. Now that the trigger is bolted to the floor and the block is free to fall, we can go back to the event graph. We're going to use that lerp node to tell the static mesh, start at Z equals 300 and over 0.5 seconds slide down to Z equals 0. Does your component list look clean now with the mesh and the box sitting side by side? Perfectly handled. That decoupling is a fundamental step in blueprint organization. By dragging the box onto the root or effectively detaching it, you've ensured the box collision stays fixed in space while the static mesh performs its animation. If you look at your components panel now, you should see both the static mesh and the box collision as independent siblings underneath the default scene root. The blueprint flight plan. Now that the block is free to move on its own, we need to gather the actual numbers for your timeline and lerp nodes. Here is the logic we're about to wire up. Point A, the start. With the static mesh selected in the viewport, check its location Z. If it's hovering above the catwalk, this might be 300 or 400. Point B, the end. This is where you want the block to stop. Since we want it flush with the catwalk, this value will likely be 0 relative to the blueprint's root. Wiring the movement. Back in your event graph, let's finish the update logic. Get the mesh, drag your static mesh component into the graph. The movement node, drag off the mesh and search for set relative location. Connect to timeline. Connect the update pin of your block fall timeline to the execution pin of set relative location. The lerp. Right-click and create a lerp float node. Plug your timeline's height alpha output into the alpha pin of the lerp. A value, type in your starting height, e.g. 300. B value, type in your ending height, e.g. 0. Final connection. On the Set Relative Location node, right-click the new location yellow-orange pin and select Split Struct Pin. Plug the output of your lerp directly into the new location Z. By splitting the pin, you are telling Unreal, keep X and Y at 0, don't drift sideways, but update Z every single frame based on the timeline. Go ahead and hit compile and save. Now when you step into that trigger, the block shouldn't just teleport or sim physics. It should slide down perfectly smooth to the exact spot you designated. Does the animation look as snappy as you hoped in the preview? You've hit on a great point. There are always multiple ways to skin a cat in Unreal Engine. If you want to keep the static mesh at a relative Z of 0 and move it from there, you're essentially shifting your point A and point B. If your mesh is at 0, the center of the blueprint, but you want it to start high and fall to that 0 point, your lerp values would look like this. A start 300, the air position. B end 0, the home position. Adjusting the heights. By keeping the mesh's default location at 0, you're making it easier to place the blueprint in your level because the bottom of the block will align perfectly with the floor of the blueprint. In the viewport, reset your static mesh location to 0. The box collision, move this independent of the mesh. Since the mesh is at 0, you might want the box to be slightly in front of it or encompassing the area where the player walks. The logic, even though the mesh lives at 0 in your viewport, the timeline plus lerp will force it to 300 the moment the game starts if using an initial set or the moment the trigger fires. The different ways advantage. Since you mentioned trying different ideas, here are 2 common ways people handle this specific height problem. Method how it works, why use it. Absolute lerp, you hardcode 300 into A and 0 into B. Very simple and predictable for one-off traps. Relative offset, you get the mesh's current location and subtract height from it. Allows you to make the block fall from any height without changing the code. The final sanity check. Since the box collision is now independent, double-check its position in the viewport. You want to make sure that when you place the blueprint on your catwalk, the box is at player height while the mesh is hidden or hanging above. If you hit play now, the block should snap to that of value and then slide down to B. How are the heights looking in your viewport? Is the block sitting where you want it to land, or are you going to have it fall through the catwalk for a pitfall effect? That makes total sense. Matching the static mesh pivot to the scene root is a pro move. It means the center of your block is the center of the blueprint. By moving the entire blueprint actor up in the level, you're essentially setting the loaded position of the trap. If the box collision extends downward from that origin, it acts like a dangling sensor reaching down to the catwalk to catch the player. Visualizing the setup. Here is how your logic is now functioning with this high origin setup. The origin 0, this is where your move gizmo is. Your block is sitting exactly here. The trap height, by lifting the blueprint in the level, you are physically placing the block at its ceiling position. The sensor, because the box collision is independent and extended downward, it's already touching the catwalk even though the block is high above. Updating the fall math. Since you've moved the entire blueprint up in the level, your set relative location logic needs to reflect that the block is already at its starting point. Relative start A, since the mesh is sitting at the root, its relative Z is 0. Relative end B, to make it fall, you actually want it to move downward relative to the root. If your catwalk is 300 units below the root, your B value in the lerp will be minus 300. Why this is a cleaner workflow? This approach is actually much more intuitive for level design. Visual alignment, you can see exactly where the block starts in your level. Adjustable triggers, you can select the box collision inside the blueprint and stretch its box extent so it always reaches the floor, no matter how high you place the trap. Final step, the connection. In your event graph, make sure your lerp reflects this new negative Z journey. Lerp A 0, the current origin where the block lives. Lerp B minus 300 or whatever distance brings it down to the floor. When you hit compile and save, try dragging the blueprint up and down in your level. Does the box collision look like it's properly scanning the catwalk area where the player will run? That 410 cm mark is a great choice for a ceiling trap. It's high enough that the player won't feel cramped walking under it, but it gives the block enough travel time to feel heavy when it drops. By setting the static mesh to a relative height of 410 inside the blueprint, you've established a clear point A. Now, let's look at how that changes the math in your event graph. The math of the fall. Since your mesh is now sitting at 410 and you want it to land at ground level, the blueprint's origin, your lerp node needs these specific coordinates. A, the start 410. B, the end 0 or slightly above 0 if you want to account for the block's own thickness. Finishing the wiring. Now that you have your high point established, here is the final chain of logic to make the block move. Update pin, connect the update execution pin of your timeline to a set relative location node for your static mesh. The alpha connection, plug the height or alpha output from your timeline into the alpha pin of your lerp. Splitting the pin, right-click the new location pin on the set relative location node and select split struct pin. Z-axis only, plug the output of your lerp into the new location Z pin. Leave X and Y at 0 so the block doesn't drift sideways. Pro tip, visualizing the hitbox. Since your block is now 4 meters in the air, make sure your box collision, the sensor, is stretched tall enough or moved down far enough to actually intersect with the player's character. If the box is sitting up at 410 with the block, the player will walk right under it without ever triggering the trap. Select the box collision and use the box extent or location Z to ensure it's dangling right in the player's path on the catwalk. Once you hit compile and save, try running through the trap. Does the block drop fast enough to catch you, or do we need to shorten that timeline duration to make it more lethal? Smart move, keeping the scale at 1 and using the box extent, the specific dimensions inside the details panel, is a professional best practice. If you scale the whole component, you can sometimes run into weird squashed physics or collision detection bugs later. By adjusting the extents, you're changing the math of the shape without distorting the component itself. Now that your invisible tripwire is properly dangling down to catch the player and your block is parked 410 cm in the air, you are ready for the final logic connection in the event graph. The drop execution. Since you've defined your A and B points, we just need to tell the static mesh to follow the timeline. Get the mesh, drag your static mesh component from the left-hand list into the event graph. The setter, drag off the mesh and find set relative location. The update loop, connect the update pin of your blockfall timeline to the execution input of set relative location. This ensures the block moves every single frame the timeline is running. The interpolation. Right-click and add a lerp float node. Connect your timeline's height output to the alpha of the lerp. Set A to 410. Set B to 0. Why we use update. The update pin is like a heartbeat. Every time the timeline ticks, which happens many times per second, it pushes out the current height value. By plugging that into the lerp, you're telling the block, at 10% of the time be at height 369. At 50% of the time, be at height 205. Final blueprint cleanup. Compile and save. Always hit these buttons before testing. Debug print. If you still have that print string from earlier, leave it in for one more test. It's great to see that true message pop up the exact moment the block starts moving. When you drop into the level now, that box collision should be waiting for you. As soon as you overlap it, the block should drop from the ceiling and land perfectly at the origin ground level. Does the block land with the speed you were expecting, or does it feel like it's floating down? No need to apologize. Blueprints are all about iteration, and keeping your setup aligned with your notes is the best way to ensure the logic follows the script you've built. By having the box collision parented under the default scene root and not the mesh, you've successfully isolated the trigger. Even if it's visually under the mesh in the list, as long as it isn't a child of the mesh itself, it won't move when the block falls. Finalizing the drop math. With your static mesh scale set to 2 and your starting position confirmed, let's lock in those lerp values in the event graph to make the movement happen. Start point A, enter your high Z value, e.g. 410. End point B, enter 0. Since the mesh is parented to the root, setting it to 0 will bring it perfectly to the floor of the blueprint. The alpha, ensure the height output from your timeline is plugged into the alpha of the lerp. Why the scale of 2 matters. Since you've scaled the mesh to 2, the block is twice as large, but its pivot point stays the same. When the timeline hits a value of 1, sending 0 to the set relative location node, the center of that giant block will snap to the floor. Pro tip, if you find the block is clipping through the floor because it's so big, just adjust your B value in the lerp to something like 50 or 100 to account for the half height of the scaled up mesh. The moment of truth. Compile and save. Go to your level editor and make sure the blueprint is placed high enough that the block starts above the player's head. Hit play and walk toward the catwalk. If everything is wired correctly, the height track will start counting, the lerp will calculate the path from 410 down to 0, and that scaled up block should come crashing down right as you pass under it. How does the impact look? Does the scale of 2 make it feel like a truly unavoidable obstacle? No apologies necessary. That diversion actually helped you fine-tune the most important part of the trap, the trigger zone. By setting the box location to -100 and the box extent to 100, you've essentially projected the sensor downwards from your origin. In Unreal, a box extent of 100 means the box is 200 units tall total, 100 up, 100 down from its center. Since you moved the center to -100, the top of your trigger box sits perfectly at the origin 0, and the bottom reaches down to -200. The final visual check. When you look at it in the level editor, you should see the move gizmo sitting at the base of your static mesh, the loaded position. The wireframe box extending down from that gizmo, acting like a long invisible curtain that the player has to walk through. Finalizing the event graph logic. Now that the physical setup is perfect, we just need to ensure the lerp is ready to move that mesh. Start A should be your current mesh height, e.g. 410 or wherever you parked it. End B should be 0, the position of the gizmo. Update loop, ensure the set relative location is being driven by the timeline's update pin. Test it out. Go ahead and hit play as you walk across the catwalk and hit that curtain of collision. The print string should fire if you still have it. The timeline starts the 0.5 second countdown. The static mesh should slide smoothly from its high point and stop exactly where the gizmo is. Does the block land exactly where you want it to, or do you need to adjust that B value slightly to keep it from crunching into the floor? That is the perfect way to visualize it. By By setting your value to represent the actual z-axis height, your timeline graph becomes a literal map of the block's journey. Locking in the drop curve. Since we've established that the block's current home, the gizmo origin, is 0 and its starting position in the air is 410, your timeline graph should look like a downward slide. The first key, the loaded state. Time 0. Value 410. Logic: at the exact moment of impact, the block is still high up in the air. The second key, the impact state. Time 0.5 or however fast you want the fall to be. Value 0. Logic: half a second later, the block has reached the origin point on the floor. Adjusting the timeline length. Make sure that length field at the top matches your end time, e.g. 0.5. Why this is better than 0 to 1. Even though I mentioned using a 0 to 1 lerp earlier, doing it your way, putting the actual height numbers into the timeline, is much more visual. When you look at the graph, you are seeing a literal representation of the height over time. If the line is steep, the block is moving fast. If the line is shallow, the block is moving slow. Connecting the output. Now, when you go back to the event graph, your height pin on the timeline node isn't just a percentage anymore, it is the actual z-coordinate. Skip the lerp, you don't even need a lerp node now. Set relative location. Drag your static mesh into the graph and get a set relative location node. Split the pin, right-click the new location pin and split struct pin. Plug it in, connect the height pin from your timeline directly into the new location Z. By doing this, the timeline is driving the block's position directly. Every frame, it tells the mesh, okay, now you are at 350, now 200, now 50, now 0. Does that downward slope on your graph look like the kind of crushing speed you're looking for? That is a rock-solid way to handle it. By inputting 410 directly into your value field, you've turned your timeline into a literal altitude controller. You aren't dealing with abstract percentages anymore, you're dealing with the actual physical space of your level. Finishing the path. Now that your key 1 is locked at time 0/value 410, you just need to tell the block where its journey ends. The impact key, right-click and add a second key. The coordinates, set time to 0.5 or however long you want the drop to last, and the value to 0. Note, since the ground of your blueprint is the origin 0, this ensures the block stops perfectly flush with the floor. Visualizing the drop, since the values are so large, 0 to 410, your graph might look like a vertical line. Use those zoom to fit icons, the arrows in the toolbar, so you can see the nice diagonal slope you've just created. Wiring it directly. This is where your workflow becomes very efficient. Because your timeline is now outputting the exact z-coordinate, your event graph logic becomes much simpler. No lerp needed, you can bypass the lerp node entirely. The connection. Drag from the update pin of your timeline to set relative location, targeting the static mesh. Right-click the new location input and split struct pin. Plug the height output from your timeline directly into the new location Z. One quick safety check. Before you compile and save, double-check that length box at the top of the timeline tab. If your fall takes 0.5 seconds, make sure the length is set to 0.5. If it's still at the default 5, the block will drop to the floor in half a second. But the blueprint will stay busy for another 4.5 seconds of silence, which might prevent the trap from being reset or firing other logic later. How does the slope look? If it's a straight diagonal, the fall will be constant. If you want it to feel heavy, you can right-click your keys and select auto to give it a bit of an acceleration curve. Those zoom and pan controls are lifesavers. It's very common to lose your keys the moment you type in a large value like 410 because the default view is only looking at a tiny window near 0. By hitting zoom to fit horizontal and vertical, you're telling Unreal, show me the whole story from the ceiling to the floor. Setting the final destination. Now that you can see your first key sitting high up at 410, let's plot the impact point. Add the second key, right-click further along the timeline and select Add Key to Curve Float. Input the impact coordinates. Time 0.5, this makes the trap feel lethal and sudden. Value 0, this represents the block hitting the ground of your blueprint. Final polish. Length, change the duration at the top from 5 to 0.5 so the logic stops exactly when the block stops. Smoothing, since you mentioned it accidentally moved, you can always reselect a key and retype the exact coordinates in the boxes at the top to make sure they are frame perfect. What the graph represents. When you look at that diagonal line now, you are literally looking at the velocity of your trap. If you find the block is falling too slowly in the game, you don't even have to change your code. you just drag that second key from 0.5 to 0.3 and the engine handles the rest. A quick tip on the ease. If you want the block to feel like it's accelerating due to gravity, select both keys, right-click them, and select Interp Mode Cubic or Auto. This will turn your straight line into a slight S-curve, making the block start its fall a bit more naturally before slamming into the floor. Ready to head back to the event graph and hook that 410 to 0 value into the mesh. Exactly. A graph with only one point is just a static value. You need that second coordinate to create motion. By adding that second key, you're essentially giving Unreal the destination for the journey. Mapping the impact. Since your first point is the loaded position at the ceiling, this second point will be the landed position. Select the new key, click on that second point so it turns blue. Set the timing time, type 0.5 into the time box. This gives the player half a second to react or fail to react before the block hits. Set the landing value, type 0 into the value box. Since 0 is the origin of your blueprint where the gizmo sits, this ensures the block stops exactly flush with the floor. Sync the duration. Don't forget to change the length field at the top from 5 to 0.5. This trims the animation so the timeline doesn't keep running after the block has already landed. The slam effect interpolation. Right now, your graph likely shows a perfectly straight diagonal line. In the physics world, this is linear movement. The block moves at the exact same speed from start to finish. If you want it to feel like it has weight and gravity, select both keys. Right-click one of them and select User or Auto. This adds tangents, little handles. You can curve the line so it starts a bit slower and reaches its maximum crushing speed right as it hits the value of 0. Back to the event graph. Once those 2 points are set, your timeline is officially a Z-axis engine. Switch back to the Event Graph tab. Drag your static mesh into the graph to get its reference. Drag off the mesh and search for Set Relative Location. Connect the update pin of your timeline to the execution pin of the Set Relative Location. The direct hookup. Since your timeline values are already 410 to 0, you can right-click the New Location pin, split Struct pin, and plug your height track directly into New Location Z. When you walk into that trigger now, the timeline will play through those coordinates and you'll see your block plummet from the ceiling. Ready to give it a test run in the editor. You're absolutely right. In the world of game design, 1 second is actually an eternity for a trap. A player can walk quite a distance in a full second, which makes the trap feel floaty and easy to dodge. To make it feel like a heavy, dangerous slam, you'll want to drop that time value significantly. Setting a lethal time value. The time, try a value between 0.2 and 0.4 seconds. 0.2s is almost a jump scare. It's nearly instantaneous. 0.3s to 0.4s is usually the sweet spot where the player sees it coming but has to react immediately to survive. The value, keep this at 0. This ensures the block finishes its journey at the origin, the ground level of your blueprint. Trimming the fat. This is a step many people miss. Look at the length field at the top of the timeline tab again. Even though your animation ends at 0.3 seconds, the timeline itself might still be set to the default 5 seconds. Change the length to match your time value, e.g. 0.3. This ensures the update loop stops firing immediately once the block hits the floor, which saves performance and keeps your blueprint logic clean. Making it snap the ease in. Since a real falling object accelerates due to gravity, a perfectly straight line can sometimes look a bit robotic. Select both keys in your timeline. Right-click one of them and select Interp Mode Cubic or Auto. This gives the curve a slight bend. You want the line to start a little flatter and get steeper as it approaches 0. This makes the block look like it's gaining momentum before it slams into the floor. Connecting the logic. Now that your timeline is a high-speed altitude engine, go back to the event graph. The height pin on your timeline is now pumping out numbers from 410 down to 0 very rapidly. Plug that into your Set Relative Location Z. When you hit compile and play, you should see a much more satisfying thud as the block hits the ground. Does the 0.3 second drop feel like it's fast enough to catch your character? A quarter second, 0.25s, is the perfect danger zone speed. It's fast enough to be a genuine threat but gives the player just enough of a frames per second glimpse to realize they've messed up. By setting that second key to time, 0.25 and value 0, you've created a very steep drop on your graph. Trimming the timeline. You're exactly right about the length. This is the most common reason blueprints hang. If the length stays at 5, the block will hit the floor at 0.25 seconds, but the timeline will keep playing for another 4.75 seconds of empty space. Go to the length field at the top of the tab. Type in 0.25. Now, the moment the block hits the floor, the timeline reaches its end and stops executing the update pin. Final blueprint hookup. Now that your animation script is finished, let's wire the engine to the block in the event graph. Execution, connect the update pin of your timeline to a set relative location node. Target, make sure the static mesh, the block, is plugged into the target input. The Z-axis. Right-click the new location pin on the set relative location node and select split struct pin. Drag a wire from your timeline's height output and plug it directly into the new location Z input. Why this is clean. Since your timeline starts at 410 and ends at 0, you are effectively saying, every frame for 0.25 seconds, force the block's height to match this descending number. One last Polish tip. Since the fall is so fast, you might want the block to stay on the ground once it hits. In the timeline settings, make sure loop is unchecked. Ensure autoplay is unchecked. We want the trigger box to start it, not the game start. Hit compile and save. When you jump into the level and trigger that collision box, you should see a satisfyingly rapid slam. If you want to add a bit of juice later, that finished pin on the timeline is the perfect place to plug in a camera shake or a thud sound effect. Does the drop look as lethal in the viewport as it does on the graph? That dead space is the silent killer of many great blueprint traps. If you left it at 5 seconds and then tried to add a reset or retract function later, you'd be sitting there wondering why nothing is happening for nearly 5 seconds while the timeline finishes its invisible countdown. By setting the length to 0.25, you've effectively trimmed the clip. The moment the block hits the floor, the blueprint is immediately ready for whatever comes next. Final blueprint assembly. Now that the timeline is tuned like a high-performance engine, let's head back to the event graph to wire up the final sequence. The execution flow. Input, your on-component begin overlap box should be plugged into the play from start pin of your timeline. Avoid play if you want the trap to reset perfectly every time. The update, drag a wire from the update pin to a set relative location node. The target, ensure your static mesh is the target of that node. The data, since your timeline track height is outputting values from 410 down to 0, right-click the new location pin on the setter, split struct pin, and plug the height output directly into new location Z. What to look for in your test. When you hit compile, save, and play, keep an eye on these 3 things. The slam, at 0.25 seconds, it should look less like a slide and more like a drop. If it still feels a bit robotic, remember you can right-click those keys in the timeline and set them to auto to get a smoother acceleration. The landing, the block should stop exactly at the location of your blueprint's gizmo, Z equals 0. The trigger, since the box collision is now independent, make sure it's positioned where the player's waist would be. If it's too low, the player might jump over it. If it's too high, they might crouch under it. One quick tip for juice. If you want to make the player jump out of their seat when it hits, drag a wire from the finished pin on your timeline and add a play sound at location node. Use a heavy thud or impact sound. Since that pin only fires when the timeline reaches 0.25 seconds, the sound will sync perfectly with the block hitting the floor. Does the trap catch you when you try to sprint through it now? That is the classic cliffhanger moment in game development. You've built the engine, the timeline, you've fueled it with data, the 410 to 0 curve, and you've trimmed the timing, but the block is just sitting there. Usually, when a blueprint looks perfect but stays frozen, it's because the execution circuit isn't complete. It's like having a perfectly tuned car but forgetting to turn the key in the ignition. While you're on your break, here's a quick pre-flight checklist of the most likely culprits we'll be looking at when you get back. The play versus play from start logic. If the timeline was accidentally triggered once during a preview, it might be stuck at the end, value 0. Using play from start ensures it resets to the ceiling every time. The input connection, we need to verify that the on-component begin overlap is actually talking to the timeline. If that wire isn't glowing, the drop command never reaches the engine. Collision settings, sometimes the box collision is set to overlap all, but the player character isn't technically a pawn or doesn't have generate overlap events checked. If they don't see each other, the trap never trips. The static mesh target, we need to make sure the set relative location node is specifically targeting your block mesh and not the default scene route by mistake. Enjoy the break. When you're back, we'll grab the multimeter, check the wires, and get that block slamming down. Ready when you are.